So our last topic here in our L'Hopital's rules section is talking about how we deal with indeterminate powers. So 0 to 0, 1 to the infinity, or infinity to the 0. And when we have indeterminate powers, sometimes we can handle these by first taking the logarithm of the function. And so we have this property here that says if the limit as x approaches a of the logarithm of the function equals a limit, then the limit as x approaches a of the function would be equal to e to the natural log of the function, or e to the limit. So if you think about what we know from algebra, previous algebra classes, we know that e to the ln of x is just x, right? We're exponentiating. So when your exponential base and the base of your log in the exponential power are the same, they cancel each other and we just get the argument. So like if I had 3 log base 3 of 5x plus 2, that would simplify to 5x plus 2 because they are both base 3. All right, so thinking about that property, what we know, here we've got e to the ln. Those are inverse operations. They cancel each other out. So we really didn't change anything. We're still taking the limit of the function. All right, so let's look at one last example here. We're going to find, let's see, the limit as x goes to infinity of x to the 1 over x. So if I looked at plugging infinity in, if I plug this infinity in for my x's, that would give me infinity to the 1 over infinity, and 1 over infinity is 0. So we've got infinity to the 0. And in this situation, what we're going to do is we're going to take the log of what we're dealing with. So I'm going to take the log, or the natural log, right? So if I do that, that gives me with the natural log, or leaves me with x to the 1 over x. And 1 over x being in the power, properties of logs, this is all back from algebra, I can take that power, put it in front of the log, and I've got x times the natural log of x. Okay, so I've rearranged this. So I've taken the limit of the function. So what I can do here is I'm going, okay, well, this is the limit as x approaches infinity of 1 over x times the natural log of x. Okay? So this is what I'm doing. This isn't the limit of the original function. This is the limit of the natural log of the function. And so if we look here, this is really the same as the limit as x goes to infinity of ln x over x. If you plug infinity in and we go to evaluate this natural log of infinity, that's going to become infinitely large over infinity. So we've got indeterminate form that allows us to apply L'Hopital's rule. All right, so if I apply L'Hopital's, I've got the limit as x goes to infinity. The derivative of ln x is 1 over x, and the derivative of x is 1. So this is the limit as x goes to infinity of 1 over x. Now I can evaluate that, and I get 1 over infinity, which is 0. So this is the limit of the natural log of the function. So we're not done. It's the limit of the natural log of the function. So by my theorem up above, I'm going to scroll back up. Since I took the natural log of the function, then I can say, well, this is just going to be e to the L. Okay? So I'll write this out kind of formally. So therefore we know that the limit as x goes to infinity of x to the 1 over x equals the limit as x goes to infinity. We let that be our function. And we said, well, I can exponentiate this, right? We took the natural log. So e to the natural log of the function, which in this case we've got e to the 0th, because that was my limit. That was my e to the L. And e to the 0th power is 1. So 1 is the ultimate answer here.